Cool. All right. So we left off right after exponents. So I wanted to leave this for later. Basically, this rule, it's not used too often, but it's used when we're doing exponential growth and we want to see when our money doubles. So what happens is, let's say you have an interest rate at 2%. What you're doing is you have to take your interest and divide it by 70. And this will tell you your money doubles after um, so many years. Oh, Lily, could you turn off your mic? Because there's a lot of feedback. Uh, thank you. You can turn it on whenever you have a question. That's fine. It was just distracting me. I'm sorry. Um, so what happens here is any interest rate, it goes by the percentage. So this one kind of confused me when I first heard about this rule of 70. Um, because I'm like, well, if you divide it by 0.02, which is 2%, it'll give you like a really big number. But what it's talking about is literally just the percentage. You just divide it by the percent. So if you get 1% interest, it'll take you 70 years to double your money. So that's all this is talking about. Um, does everybody understand it okay? Looks good? Cool. So what this says here, so for example, let's say we have 0.05%. So we're going to have to divide 70 by 0.05. And I can kind of verify it. Let me pull out my calculator here. So if I do 70 divided by zero point 0.5, it should take us 140 years to double our money. So let's take a look at this. So the estimate is about 140 years. That's their estimate, but the actual value is this much. So you can see it's off by a little bit. So if we wanted to actually calculate that, that's what we learned Monday, where we have to use this PERT. So we would type in our principal, which in this case is 1. We're just trying to figure out when our money doubles. And we want our this, we don't know what our t is. We don't know how much time, but we would put 2 here because we're trying to double it. So let me kind of pull my pen out. I didn't set up my tablet yet. So let me sign in. Oh, not that one. It's gonna yell at me saying like you don't have the paid version. Yeah. Sorry guys, I usually have this ready. I forgot to set it up today. Let me sign out of here. Sign in with Google. Sign into my private. Yeah, that's fine. All right. So basically, if we were trying to solve how to double it in real life, what we would have to do is we would have to do 2 for our answer equals ER, and we're solving for T. So we haven't learned about logs yet, but we would have to use logs to figure out the real answer. But if we want to just double our money, we can just use this rule of 7 rule. And we'll learn about logs in the next unit. But for this one, they're just showing you this cool little trick to figure out how long it takes to like double money or double a population if you're given a percentage growth. So here, so if we're doing 2%, remember 2%, their estimate was 70. So 70 divided by 2, so it's going to take 35 years for something to double. The actual amount would be closer to 35 and this fraction right here. So this is actually a pretty good estimate. So our estimate for 1% should be 70 years to double. But for the actual amount, it'd be like 69.66. So it's pretty spot on the 70 rule. So this part's pretty simple, pretty straightforward. So this comes in handy when we're dealing with something like Halflife. We want to figure out basically the opposite when something cuts in half. So Half-Life, um, if you guys have ever heard of carbon dating, like when they figure out when fossils get older and stuff, they use this thing called Halflife. They figure out the carbon 14 natural. Normally, carbon has 12 molecules or 12 electrons. Sorry, it's been a while since I've taken my chemistry. 12 molecules. But when we're talking about carbon 14, it has 14 electrons, and those slowly wear off over time. So we can use that to figure out how old something is by using this formula. How much carbon's left? Try to figure out how much the original one was. Use this formula, and then we solve for t. So if we're solving for this, we have 500 grams of that carbon. This we know that the half life is this many years, and we figured this out. So this one, in order to find actual carbon, we would have to know the amount there was originally, how many years it is and stuff. So we would use logs. So right now they're kind of just introducing us to the concept um, of half life. So let's get into the actual problem. So this one just gives us examples. We start off with 50. Half life is 1600 years. So the half life is 1600 years. Only 400 years have passed. So how much half life would exist after 400 years? So this tells us like future predictions. It's not an actual like how many years were there originally. This is like future. How much would this carbon have after a while? And then I don't know why that keeps getting stuck there. All right. So if we're doing this, this tells us that after 2017, an earthquake hit Japan and damaged radioactors and had high. So this is just a different type of element. Don't worry about these numbers. This is just talking about the electrons. We don't care about the electrons. We're just talking about the numbers. So the half-life is 8 days. And it wants us to know how much would exist after 30 days. So we're going to put 30 divided by our half-life, as they did over here. So you guys can always refer back to these slides if you need it. So see how half-life's on the bottom? Use my highlighter. Half-life's here at the bottom. And the actual number of years we're trying to figure out goes right there. So always use these in case like you guys want to study and stuff. Always come back to these just to make sure you're, you know. But anyway, so we're trying to figure out this. So our half-life is 8 days. We're going to do this. We know that our exponent is 1/2 because it's getting cut in half. So just pretend my 1/2's bigger and this is an exponent. And we're trying to figure out, so the original amount was 2.5. Okay. And we want to figure out how much is there going to be after 30 days. So what we're going to do here is, you want a scientific calculator? Let me turn my scientific calculator on. It usually takes a while. I think Desmos has a scientific calculator, if I'm correct. Desmos.com calculator. So in case you guys don't have a scientific calculator at home, I think Desmos does have. Oh, that's a graphing calculator. Desmos scientific calculator. So you can always use this one. I'm not sure how accurate it is, but I'm going to compare it to my Texas Instrument one. So 2.5 parentheses. You can put 1/2, but I'm going to put 0.5 because 1/2 is the same thing as 0.5. And then we're going to raise this to the power of, um, what was it? 30 divided by 8. So we're going to raise it to the power of, oh, this is why I don't like the Desmos one. They want an exact number. You can't put a fraction in here. I think I did this last week too. You can't put a fraction in here. So I would recommend trying to find a more accurate calculator. You could do like 30 divided by 8. 3.5. So you can just set the exponent to 3.75, and that should give you the answer right there. Or again, if you guys have a different calculator, let me know. That way I can like tell other students. But I'm just gonna do it on here. So I'm gonna do this 0.5. And then what I'm gonna do here is I'm gonna raise this exponent, use parentheses to show 30 divided by 8, and I get the same answer. So it depends on how you guys want to do it. If you guys really want to use the Desmos calculator, you can just use this. Just remember, it's not going to let you do the fractions. So I'm getting, there's going to be about 0.18. It looks like there's some round off error, so it should be 0.19. Does this make sense to everyone how to set it up? Cool. All right. So continuous decay. Continuous decay is similar to continuous growth. So remember, continuous growth was just PERT. The only differences are growth rate. So if it decays at this, what we're going to do is we're going to put a negative exponent right there. So our exponent you'll see is negative. Let me use this. So that's the only difference is our R. So everything's still the same. This is continuous though. We'll go into discrete growths later. Or actually, we already did it. Sorry. But yeah, this is how you would do continuous decay is with the E number. So here, if we're doing use the carbon life, so this is our life to prove that to prove or disprove the estimated age of the hypothesis. So there's a hypothesis here between this year and this year, George on Earth. So these years we don't need so much. We just want to know the testing. So when I'm reading this, I'm looking for my years because I know this is a years problem. About 75% of the original carbon was there. So what this is telling me is that we have 0.79 left. We need to figure out what we had initially. And then this right here is E. Our rate of growth would be, where is this? Archaeologists measured this out. So they're saying that it's this old. And we're using this half-life. So remember, our half-life goes on the bottom. And then the number of years we're trying to say that happens, we want to put that on the top. Because basically what's happening is our rate is equal to 1 over 5 this, and then we're going to multiply that by our time. So that's how come it ends up looking like we're dividing a fraction. And estimate the number of dates. So in other words, we don't really need a number here because we're saying there's a percentage. So it decreased, right? So, oh wait, this is Half-Life. I'm so sorry, guys. I'm like writing all this stuff down and it's Half-Life. Half-Life formula was uh, 1/2. And then we're going to use the exponent. They confused me because they did the other one. I'm so sorry. So this one, I was wondering, I was like, that's so weird. 1900 over this. I just used the wrong formula. Okay. So we're going to try to prove if this is true. So if this is true, we can use the half-life formula, this half, and then we're doing this over the half-life, and we should get this 0.79. So what you would do here, again, when you're writing these, try to use your equation editor. I think it's a little better to use it, the equation editor, than to use all of these symbols. So you would do 7.9 equals 1/2 fraction 1/2. We're going to use our little exponent. And in that exponent, there's another fraction. 1900 I know I've gone over how to do this several times. I'm just doing it right now so you guys can remember, just get a refresher on how to use the equation editor. So we're doing this. We're trying to prove if this is true. So what I'm going to do is going to do this, and then I'm going to figure out if this is true or not, if it's equal or not equal to. And if you guys need the not equal to sign, it's right there. I just like writing in the pen better. So here we're going to do our 0.5, and we're going to raise this to the power of 1900 divided by 57, a long half-life, 5730. So yeah, there's about 79%. So from here we would write 0.79. So we would write a sentence here just like this proves it. This proves it is true. Is this making sense? I know I kind of jumped the gun and I used the wrong formula, but other than that, everybody good? You guys can type in the chat if you want. Cool. All right, let me erase this. Where's my little board? There it is. All right. Cool. So moving on to this one, what percentage of carbon is left after this? So we're going to have to use the original half-life here. So when we're writing this formula down, we would write it down as 1/2 of this 5,000 divided by our half-life. So I'm not going to go over every other problem. I'm just going to set this up. But now you guys know how to solve this. So you would do this, and it would give you some kind of decimal, and that's what you would do here. We have a lot to cover, so like I'm just going to show you guys how to do it. Sorry, in case you guys want to screenshot it. Or remember, you can always rewatch the video on the Google Classroom or on YouTube later. 7. So you would plug that into some type of scientific calculator. The next one, oh, self-evaluation. So after that, you're done with this section. Let's move on to the next one. Does everybody understand Half-Life okay? All right, cool. So imagine you're a chemical engineer. So this is talking about the different types of chemicals that we're seeing here. So this is why exponential growth is important. So we can see how long it would take. So view this scenario. So in this, guys, again, the videos and stuff, just make sure you read them just to kind of get an idea of all this information. But this just tells you like how long it would take to decrease over time. So I want to go more into the math rather than all of these other things. So what it's talking about here is just talking about the nuclear safety. So knowing the half-life of how long these chemicals are active are part of the reason why we do so much safety things on nuclear power plants. So um, it's very like the decisions they're saying here are challenging just because it takes so long for these chemicals to go away. So that's how come like using these formulas, you can see it takes like 1,000 years for just some of it to go away. So this is just going to be talking about our mathematical models for exponents and stuff like that. So again, guys, read this all through. I want to get through more of the math. That's why I don't read these as much as you guys can by going through it. So the next one, it's talking about like a learning curve. This is a different type of exponential growth because remember with exponential growth, it never touches the zero and it keeps growing on forever, right? This one's kind of like flipped over. What's happening is we have a negative uh, rate of change, so it kind of flipped. So what's happening is this flips over to look like this, and then it's also flipped over another way. So our asymptote's here and it flips this way. So this is what it's talking about by a learning curve. Usually when you're trying to learn something new, it's hard. You're learning a lot. Like at first you know nothing, and then you go, but as time goes on, it becomes harder and harder to learn the new concepts until eventually you theoretically get to the point where you know everything. So this is just kind of showing us our model here. We have this m, which is the maximum value. The negative c right here kind of tells us where that's going to be. So that's what this negative c flips it over to be like this. This negative flips it over, or I'm sorry, both negatives are like this. The first one flips it over this way, the next one flips over the other way. So that's how come we have two negatives in this expression. All right. So moving on, this is just kind of showing you the learning curve. So at first, like after so many days, the percentage, so this is our percentage rate of growth. So after 6 days, all of a sudden it's 4 feet that this high jumper is jumping. After 12 days, they're jumping a lot. Like 0.3 is a lot when you're talking about feet and you're talking about a high jump. So if you guys don't know what a high jump is, what's happening is there's a bar and they keep raising this bar higher and higher and the person's jumping over it. So what's happening here is when we look at the first growth, because this is always 6 days. So at first, probably couldn't jump at all. Then there was like a 4.3 gap. And then after this was only a zero point 0.3 gap. And then after that, this was a 0.9, or sorry, 0.27. And then from here, there's only a 0.23. So we can see that it keeps decreasing a lot more and more over time. This one is 0.21. So these learning, it's going to keep decreasing more and more. And I guess we can probably ignore that, but there is this gap that's going less and less. So the more time this person keeps jumping, the less it's going to increase. So that's what it means by this learning curve, this flipped over function. And then here, this is called a logistical curve. So this is just saying that these types of curves are usually when it grows exponentially and then it starts to what's called plateauing. So just like a learning curve, there's a point where you kind of just plateau and you can't learn about a subject anymore. So you would have to learn about a different subject. This is the same thing. It's going to have this exponential growth, but it also plateaus here. And this one's a little more complicated because it has your maximum value here and then it's being divided there. So this logistical growth is used for different types of things where it accelerates and then it's going to start decelerating right away. All right. So here, let's read this scenario. So here, oh, how appropriate. There's a contagious virus. The school has 200 students. So what's happening here, this could not be happening at a more appropriate time. So viruses do have kind of this plateauing effect. It's this idea that exponentially it's going to grow, and then in theory, what will happen is that growth will just start decreasing more and more, or decreasing less and less. So at first, every all of this, it feels so weird talking about this. I wish they would have done a different subject. But what's going to happen is we're going to have a lot of people getting this virus over and over. But then after a while, the whole population will start getting it, and then they'll start decreasing less and less. So this is kind of what they talk about when they're talking about this uh, flattening the curve type thing. They want this rate of change to grow less and less. So by doing the practices that we're doing, it should theoretically decrease this exponential growth. So that's what it's talking about here is as it's increasing, eventually as we get closer and closer to that population, it'll start the rate of at which people are getting infected starts decreasing. All right, so moving on. And then there's this. Wow, they keep bringing up the bell curves and stuff like this. Um, so there's this idea of a bell curve. This idea of a bell curve is a different type of exponential growth. So it starts at the beginning where not that many people would stretch out. Like, let's say we were talking about intelligence, for example, or, oh, this one's actually more appropriate, SAT scores. So most of the people will be right here in the middle. Like, if everybody took the SAT, in theory, most of the people are going to get this, and less people will get like a really bad score. But also, that comes with the caveat of less and less people would get more of a perfect score, because in the SATs, the perfect score is 800. So being close to 800 is just as likely as being close to 200. So this is just this idea that the majority of the population is going to be right here in the middle, and everything else is kind of be right here on the sides. And that's represented by this formula here. So there are going to be a bunch of these formulas. I don't think the mastery test quizzes us on a lot of them. I know there's Halflife in there, and I know there's the rule of 70. So make sure you guys are studying that for the mastery test for this module. So Newton's cooling thing. We kind of did this with the little coffee, where they kind of gave us the coffee measurements, and we obviously couldn't measure it in an actual experiment. But Newton's cooling model is this idea here that it's going to start, the temperature starts decreasing exponentially. And this is the formula for that. So this is a good way to kind of calculate formula when things are cooling down. That's basically it for this one. So now we're going to be looking at that actual formula. So when you guys are doing this, just remember to always click and submit or write this down on a piece of paper. That way you can always go back and forth here. So we're going to use this model here. So what I'm going to do is I think I'm going to cheat. I think I can do this way. Plus 50f minus, or I don't need to put the f because this is all in f. 50f minus that. Where's the actual model? There it is. So the temperature equals the rate of change plus initial temperature minus the rate again. And then e to the negative k t. Did you guys want me to go over the variables on this? I'm sorry, I didn't even ask. Or do you guys think you got it? You guys can type yes or no in the chat. Oh, you're not sure? Okay. So I'll explain the variables. I'm sorry. I like went through this really fast. So the R here represents the initial temperature. So this is the temperature that we're talking about. The K is this constant, which it depends on what room you're in. Like for example, if you're in some place that's very windy or ice or insulated, so like in a fridge and stuff like that, this K is going to be different for depending on every situation. I'm sorry. And I thought that was weird. Initial temperature is actually this one. So let me use the highlighter for these. So initial temp. So this T naught is our initial temperature. Our R, I'm going to use this, is the surrounding temperature, everything that's around it. So let's say you have something that's really hot, but the temperature around it is very cold. So this right here is what the temperature starts off at. This is the entire temperature around it. And this just represents the condition that we're in, and T just represents the amount of time. So this is going to tell us the temperature that happens that's going to exist after a certain amount of time. So we have the condition is our K, T is the amount of time, and R is the temperature around us, everywhere around us. So in this case, they're saying that we're going to use this constant right here. So let me see if this formula actually goes to the next slide when I click the next slide. Perfect. That's what I was hoping would happen. So I'm going to use Newton's law of cooling to kind of make this go down. So here they're giving us our K, the temperature around it. So we're literally just plugging this in, and we want to know how much the temperature is going to keep decreasing. So what we're going to want to do here is we're going to want to make an X and Y chart. X, Y. And we're going to plug in 1 hour, 2 hours, 3 hours into this formula. So this is the part where a graphing calculator comes in pretty handy, because what we can do here is, so let's identify our variables. And I recommend typing this in when you're typing it, be like R equals, so the area around us equals, what's room temperature? The fridge is that much. Okay, so in this case, we're going to use 40 as our R. Our T naught, I'm not going to go into the equation editor, but just pretend that's T naught, is equal to 70. So our initial temperature is 70, and our K is this 0.4. So K equals 0.4. And now we can create our formula. So the way I would create the formula would be T equals 40 plus our initial temperature is 70 minus our initial temperature times E, negative 0.4, and we're going to do 1 hour first. So I'm going to show you why it's kind of cool to have a scientific calculator, because what we're going to do here is we're going to do 40 plus, okay. Oh, you know what? I think I can make this calculator smaller. Cool. All right, so I'm going to do 40 plus parentheses 70 minus 40. So in other words, 30. You technically don't need the parentheses. You could literally, if you wanted to, do 40 plus 30. And then we're going to do E. So second E. And then we want to do this negative 0.4 times 1. And the reason why I'm not just doing 0.4 is because of what I'm going to do next. So this, what happened here? What do you mean syntax error? You know what? I bet you it's because I didn't do the times right here, or I didn't use parentheses. These calculators are picky sometimes. Second, where's the insert button? Insert, negative. Got you because there's not a time sign right here. Oh, oh my gosh. I really hate how calculators don't know the difference between, or calculators know the difference between a negative and a minus. So that's what was happening, is I had a negative there instead of a minus. So I probably didn't even have to do this little times there. So we're going to have 60.1. So on your little chart, you'll put like 60.1 there. And then you're going to, if you have a graphic calculator, you can re-enter the equation, but just change this to a 2. And then all of a sudden, you see that dramatic drop. It's just dropping really fast. So it automatically dropped 7 degrees right there. So it dropped 10 degrees. Now it's dropping 7 degrees. So that drop's going to decrease even more when we get to 3 hours. So now it only dropped 4 degrees. So what's happening is first we drop really fast and then we start slowing down that drop. Is this making sense, guys? Yes, no, maybe? Cool. Maybe. Okay. So basically, like if I were to graph this, we would have the one, we would have the what was the first one? 60. The next one was oops, let me make that go away. 43. So at 2 it's 53 and it keeps decreasing. So if we were to graph like a bunch of them, we would see this graph going down here. So just make sure when you're doing your answers, guys, you have this little X and Y chart. And I'll show you what that kind of looks like. Enter. So you would do a table. Insert table. You want 1, 2, 3, but you want rows for your X's and Y's. So you want a 2 by 4. Did it insert it? 2 by 4. There we go. And then you can type in your X and your Y. Type in your 1, 60.1, whatever. So again, if you guys don't have a scientific calculator, try Googling it. Sometimes Google has a pretty good scientific calculator. You're definitely going to need one for this mastery test. Desmos has one. I'm surprised Google doesn't have one. GeoGebra. Oh, GeoGebra has one too. So just Google one. That way you can just do it on your Chromebook if you need it. All right, and give me a second. Let me go back to our growth. Did that kind of clear stuff up for you guys? Nick, when did you get here? Oh, okay. Is what I'm saying making sense stuff? Yeah. Okay. Okay. I mean, go back and rewatch the YouTube video for what you missed. But we're using this formula right here. You'll see on the video like what it means. So now it's like, what is the ideal temperature? The ideal temperature for soda is this. So what it's telling us now is at what time approximately will we do this? So what they want us to do is since we did this for 2 and 3, oops, not that, definitely not that. Calculator. Here we go. So if they want it at 50 degrees, we want it somewhere between 2 and 3 hours. So after 2 and 3 hours, that's when we can take our soda out of the fridge based on this temperature. All right. And then, so now we're going to talk about these types of graphs. So logistic growth. So remember, this one was a learning curve. So we know it's not A. This one was just exponential growth. This one was exponential decay. And yeah, you probably noticed I skipped C on purpose because this one is the logistic growth where it grows a lot. Like the example they gave was viruses, which I feel is really on the nose. It grows a lot, and then as it gets closer and closer to the entire population, it starts plateauing. So our answer for logistic growth would be C. All right, and then just remember, guys, watch this video. Usually, they do talk about all of the things that they want from the types of growth. Watch the video, or I would go back to the tutorial and write down the formulas. So write down this formula, for example. Go back on the tutorial when you're doing it. write down the formulas. Any formula you see, I would just write it down. That way you have them for the test if you need them. And if you need, again, if you guys ever need help kind of understanding what the formulas are, or if you don't pass your test, just do the appointment with me. So that's it, guys. Like, that's going to be our unit one. Um, any questions? Let me stop the recording right now.